Good afternoon. We're just going to wait a couple of minutes just for a few more people to join, and then we will get going. So yeah, if you just hold on for a minute or two, and we'll get started. Okay. So thanks everyone for joining us. Hopefully you can all see my screen currently. If you've got any problems, do let us know in the chat. But a warm welcome to today's webinar. Runtime is about 50 minutes, so there'll be some time for questions. And we'll also make a recording available for you post-event if you do want to share it with colleagues. All microphones are muted for attendees, so you won't be able to speak, but do put your messages in the chat and we'll cover them towards the end. So by way of introduction, I'm Rob Shropshire and I lead the sales and marketing side of Origin. I won't be doing a lot of the talking today, but will be your point of contact moving forward if you do want to chat with us further. I'm really pleased to be joined by Tim, who's also just on camera. He works alongside me and has been supporting our customers and training them on the solutions that we provide for the last 10 years or so. So a good person to have on today's session. And he's prepared a demonstration of the software for us, so you can take a bit of a closer look. In terms of short agenda, I'll briefly introduce Origin Engineering and what we do, how we work with Altair, and we'll then briefly discuss the challenges we think prevent more businesses from not doing their own moldflow simulation before introducing you to the product and what we're showcasing today. And then we'll go straight into a demo for you before wrapping up with a short summary and time for some questions. So in terms of Origin, we're a UK-based reseller of Altair solutions. So we provide the support and train customers on how to use the manufacturing simulation solutions. We focus specifically on solutions that help companies to essentially identify defects in the manufacturing process. So today we'll be talking about mold flow, but we also operate in casting, forming and 3D printing use cases, and also provide some Altair solutions which are more generic, I guess, product-based simulation, where we're looking at things like stress analysis, motion dynamics, fluid flow, and thermal analysis. So hopefully we're all in the right place today in terms of interested in injection molding, but worth you being aware that we do many other types of simulation as well. So there's no doubt a lot of opportunities for companies adopting simulation, but it's certainly not without its challenges. And I think it's probably worth covering what we see as the top three. The first is really licensing costs. Many companies just can't justify the cost of moldflow packages. They're very specialist, they do a very specific thing, so they tend to be quite expensive. And it's not uncommon for companies to be spending 20,000 plus for a seat of software. And especially if these licenses need to be shared or accessed by multiple people, it can get quite expensive quite quickly. So Altair provides all of the tools that you need, hopefully at a much lower price, but also gives you access to other tools which you might at the moment be paying separately for. So for example, FEA analysis or optimization or thermal analysis are all bundled in the same product suite, as well as other manufacturing simulation tools that cover things like 3D printing or casting or metal forming. Another key roadblock is typically companies don't think they've got the right skill set, or they don't have the time. So Altair only takes a day to train. So with all of our customers that have adopted these tools, the usual training package is a day. And after that, typically you're up and running and able to run simulations independently. Another thing to note is that with our solution, meshing is very, very automated. So typically a lot of the complexity is around understanding how a part meshes and perhaps having to sort of spend a lot of time fixing geometry errors. So with our software, the meshing is very hands-off, really. So all you really need to do is set up the problem and press go, and you should, in theory, get results relatively quickly. Now, we're not saying that you shouldn't be doing any outsourcing at all. Simulation experts are there for a reason. But we do feel that there's many opportunities, especially with the customers that we speak to, where if they would have just done some initial fill analysis or some initial mold flow simulation, they would have been able to get things right much earlier, as opposed to sending that design off to a toolmaker, realizing it's not going to work, and perhaps having to do rework of tooling and design. Another issue in simulation is usually down to getting the inputs right for the simulation. So one of the key things here is making sure that what you're doing on the machine matches what you're doing in the simulation. The other thing, of course, is making sure that the materials that you're actually using match up with the simulation package. So we do have quite an extensive library of materials to choose from, but also access to a much wider materials data center if you need some specialist plastic. So we can work with you really to make sure that the simulation that you're running is actually matching what you're doing in reality. In terms of customers, it's a trusted solution. We've got customers using various different manufacturing simulation tools, but I think what's also interesting here is the stage in the injection molding process they're at in terms of a company. So we work with some companies that are, I guess, the designer of the injection molded component. So they're going to be much more interested in perhaps optimization opportunities of design, getting some simulation done early. And then if we move through, we've got the actual tool maker and the actual injection molding companies themselves, where they don't really have a say in the design of the part, but they do need to make sure that the method's fit for purpose and it comes back defect free. So depending on where you're at and what you're doing as a company, you should still see some relevance to the software. So when we talk about Altair, it's important for you to understand we're not just talking about simulating the injection molding process. We're looking at the whole of the design from end to end. So Tim will cover this or some of this, but it might start with the actual design of the actual part. Are we doing some quick fill analysis on our actual part design to make sure that it will fill? Or have we taken advantage of optimization? So have we been able to do some rib optimization? Or have we looked at opportunities to lightweight the part? Now, all of this is fine in terms of trying to improve our design and hopefully reduce our material cost, but we also need the ability to run simulation on that optimized design. And at this stage, we're not talking about the injection molding process, we're talking about the part itself and how it's going to perform in the real world. So can we put some load cases on the part that we've designed to make sure that it doesn't move too much or it stands up to the loads that we're going to apply to it? Do we need to see it move and incorporate some motion dynamics? So all of that, again, is part of the Altair suite. And then finally, of course, we're going to do the conventional injection molding simulation, where we're really going to sort of flow through into the different areas, the filling, the packing, the cooling, the warpage, and to see what defects we might be able to see. And then again, go back perhaps in an iterative loop to refine the method or the design. So if we take that a little bit further, when we're now into that end piece, talking about the injection molding process, we're asking, will it fill? Is it a nice flow? Are there areas that don't fill? How long does it take to fill? Then we're looking at what defects we might be seeing. Are there air chaps? Are there sink marks? Is there warpage? With the end goal to come up with a method, of course, that hopefully uses the least amount of material and causes the least amount of defects as possible without compromising on the core function of the product. So I did promise I wouldn't say too much because I know you're here to watch the demonstration. So I'm going to play the demonstration now that Tim has prepared for you. Again, feel free to ask you questions throughout. And then we'll come back on, cameras back on at the end of that demonstration, just to do a quick wrap up and also do a bit of a summary.
Thanks for the introduction, Rob, and hi everyone. Again, thank you for joining the webinar. Over the next 30 minutes or so, I will be showcasing and introducing you to the Altair Inspire and the Inspire Mold tool. The Inspire tool, which is what you're seeing on screen at the moment, is what I'll be showing first, and showing how this can aid us in our design for injection molding, specifically around rib design. So ribs are obviously important in numerous components for sort of adding strength, reducing displacement. In injection molding, they might also be used to reduce potential warpage. However, sometimes these are maybe over-designed, over-engineered, adding unnecessary material and weight to parts. By using a tool like Inspire, we can use optimization to predict the best rib design and placement of those. So this is what I'm going to be demonstrating first for the next 10 minutes, and then we will jump into the Altair Inspire Mold tool, where we will show the manufacturing simulation for injection molding, ensuring that the parts that we make can be made without defects, hopefully first time, and then that allows us not to worry about things like costly tool reworks if something goes wrong. So the example that I'm going to be looking at is like sort of the handle for a consumer electronics device. In this instance, it's sort of an infrared temperature detector. But the same principles can be applied to any part, whether that be medical, automotive, or any part that uses ribs. Our aim is to obviously reduce the amount of ribs used, thus reducing material, but also try to match or be within a limit of the displacement of the over-engineered rib. So first, let's set up the model without any ribs to give us a bit of a baseline and show the effect of actually what these ribs are doing. So this is the part, which you can hopefully see is sort of a handheld sort of casing for a consumer electronics device. I'm not going to be showcasing the full capabilities of the Inspired tool, as we just don't have time, and obviously are following a specific agenda. But if you do have any questions around the tool, just put them in the chat or reach out to us, and we're happy to answer anything. So for simplification purposes, I'm going to just remove the top half and just focus on the bottom handle. This will be sort of molded in one piece though. In the structure tab of Inspire, I'm going to first define a material. Obviously this is going to be injection molding, it's going to be a plastic. So we've got a number of materials predefined. I'm going to specify ABS. But you can create your own materials or you can import them from Altair, Altair's material data center as well. So there's a number of materials hundreds of materials to choose from. So now that I've set up the material, I can set up some constraints and forces. So I'm going to first set up my sort of supports, and I'm going to say we've got some supports in this area, in this area, and one more, let's say up here. Obviously you can constrain your parts where they need to be. Now that's set up, let's apply a force. I'm going to apply this force to the grip area, and I'm going to apply like a distributed force to these three faces, and I'm going to apply a force of 250 newtons. So this would be, a person really squeezing, really exerted themselves on this part. Probably not how it would be used, hopefully, most of the time, but we do need to ensure it can hold up to this, as obviously we can't guarantee how these things are going to be used by people in the real world. So we can now actually run this and get some results. When we click run, we've got two solvers. We've got the SimSolid solver or the OptiStruct solver. The SimSolid solver is a rapid sort of meshless solver. OptiStruct is a more traditional mesh-based solver. Obviously, there's benefits to both. For the purpose of speed, obviously, I'll be using the SimSolid solver. I'm going to click the run tool, and generally within this sort of model, within 10-20 seconds, I will actually have some results that we can load and view. So I can see that it's finished already. I can import my results, and I can get an idea of the displacement of this part. So I can see my max displacement is around 26-27 millimeters. This is quite a bit actually on this part, because I think the part is actually only around 45-50 millimeters in width. So a fairly decent amount of displacement without ribs. We can sort of visualize that displacement. This is sort of underscaled at the moment. or under exaggerated, and we can see that's 0.2. We can set that if we want to true deformation, and we can see that looking at it, most likely the part is going to fail. We can look at other result types. I'm not going to go through all of this, but I can look at factor of safety and clearly see that this part is failing. So that's without the ribs. So now let's show a part with what I'd consider maybe over-engineered, over-designed ribs. So we can see that here. Exactly the same thing. Let's go for the same setup. Let's change our material to ABS. Set up exactly the same constraints and forces. So let's constrain it there, there, and there. And now set up our forces. And running this again using that SimSolid solver. And let's see the effect of these ribs and what they are doing. So again, very rapid results. We've got results. So we can see that our displacement has dropped from 27 mil to around 1.7 millimeters. So the ribs are doing exactly what they're meant to. They're doing the job. But now we can ask the question, are they over-engineered? Does there need to be as many? Can we reduce the weight and make it lighter? Maybe this makes it easier to carry. And maybe by reducing material, can we save on costs as well? If we're making thousands, hundreds of thousands of these, reducing the amount of material is always a good thing. So to study this, we can set up an optimization study. So I'm just going to open up a part so that we can set up for optimization. So in this one, we can see the setup is complete in terms of, obviously I've defined my force and defined my constraints exactly as I had before. But we can now see that we've got this brown area, which is designated as our design space. So this design space is the area where the ribs were and where the optimization will take place. I don't want to remove any material from the outer shell or the casing. And I can also set up shape controls for optimization. Because we're purely doing the rib optimization, I'm going to use the extrusion as my shape control. So I can specify this, and then I can specify sort of a draw direction. So we can see that there. Then we're ready to run our optimization, and here we can specify our objectives. So I'm going to use my objective as maximize stiffness because I want to reduce the amount of displacement. We can specify a mass target, and then we can also choose thickness constraints as well. Your ribs might need to be within a certain limit of maybe the thickness of the part. So you can set these up as well. So I might say, okay, I want it to be a minimum of 2 mil, a maximum of 3 mil, and that allow me to design them within those constraints. You can choose to include gravity. We can study multiple load cases, but when you're ready, you can hit the run tool. This isn't using the SimSolid solver. Optimization is using the OptiStruct solver, so it does take a little bit longer than a few seconds to actually get results. So I'm just going to open one that I did earlier and show you the results. I think I've just opened the wrong file. Let me just open the right one. So this is the results that we've ended up with. So you can see the optimized shape. So we can see the optimized shape that we've ended up with. This is obviously optimized based on the forces and constraints that I've applied. We can play around with the thickness of these. Obviously, again, the thickness will be defined from your minimum and maximum constraints that we set up in the results. But we can use these as a guide. I mean, you can use this. You can export this straight away as an STL model, or you can wrap a surface around it. Or we can use this as a guide, and within Inspire itself, we can use our sketch tools and geometry tools. or within your preferred CAD system, you could use these as a guide and apply any of the design considerations that may be needed, and then create your ribs that might look something like this. So you can see, similar to my results, I've now created some ribs that are, again, using the optimization as a guide. Maybe again applying some design considerations. Maybe I want my ribs to be all the same thickness and those sort of things. And we can go through the setup again. So you can see I've set this up exactly the same as before. So I've got my forces, make sure my material set to ABS. Let's just double click on this force, make sure it's set to 250. So this is my new rib design. In terms of like weight reduction, the old ribs, I've reduced the actual weight. I've done a quick measurement. Obviously I'm not showing this, but they're about half the weight of half the mass of the initial ribs. So I've reduced the actual rib weight by 50%. We can now run the analysis on this, and let's just have a look at our results. So initially I think we were on about 27 mil with the initial ribs, and I think it was about 1.7 mil with the over-engineered ribs. So here we can see our max displacement is 1.8 mil. Again, you might have to work within a certain limit. You might need to get under 2, but you're 0.1 of a mil away from the over-engineered ribs with 50% less mass of the ribs. So reducing material usage and getting very, very close to the over-engineered ribs themselves. So that's just a quick overview of Inspire, and hopefully showing how this can be used for rib design, which is very useful in injection molding. Now we're going to jump into Inspire Mold and show you this part now being sort of set up for manufacturing. So now we're into Inspire Mold and the molding simulation side. So this is obviously to ensure our part is manufacturable and that we can minimize or reduce any potential defects such as air traps, weld lines, sink marks, warpage, and many more. Inspire Mold has 2 modes. It's got a quick mode, which you can see here, and it's also got an advanced mode. So we're going to be taking a look at the quick mode first. All Inspire tools run on the same UI user interface, so moving between them really easy. And obviously the user interface itself is sort of very friendly, lends itself to quickly being able to pick up the software, set up models, and get some meaningful results. The workflow in both modes is left to right. Start on the left hand side, sort of work your way to the right. So first of all, I'm going to actually import my part, and I'm going to go into the quick mode. We'll look at the advanced mode very shortly. So let me just open up the part that we were previously looking at. And hopefully you can recognize it. So this is the part. As I mentioned, the workflow in both is left to right. So the first thing is to designate part cavity. So this is basically picking the part to use. So I'm going to choose that, and then first we can define a material. We can define a plastic type and then a grade within that group, so you can see all your different types of plastic, and then within those we've got a number of different grades of material. So these are all the predefined ones within the software. Again, there's a number of these, and then again there's many more that can be downloaded via the Altair material data center. If you have a specific material or a specific grade maybe made by a certain manufacturer, a lot of these can be found within the Altair material data center. If you do have a specific type that you've done material testing on, and it's specific, it's unique to what you do or something, then you can input these properties into the software here to actually use those. So I'm going to choose again just an ABS PC. Again, for your part, you may be thinking about, which material to use. Maybe you're deciding between a grade of nylon or ABS. Obviously, using simulation, may help you decide if one gives you better manufacturing results than the other. So that's another good reason to use manufacturing simulation. So we're going to use ABS PC, and the next step is to set the mold opening direction. So this is a great tool also to check for draft angles. So you can see, if I just move this into the middle, you can see you've got your demolding angle. You can obviously change that to whatever. You can see areas that are safe, bottom safe, and then any areas that maybe haven't got enough draft angle or maybe might cause issues. So we can look on the underside and we can see that most of it is blue. We can see that whoever designed these ribs didn't add any draft angles. So maybe that's something to look at if we want this part to be able to be removed from the mold. So once we've set up our material and defined our mold opening direction, we can move on to gating. So we can manually create gates, basically place gates wherever you want on the software. You can obviously apply multiple gates as such. Really easy to do like that. You can define gates, so designate any areas of gates. So if you have imported your part and you've got gates on it, you can designate that, and you can just specify an injection point. But another tool that we can use is the gate optimization tool. And this allows the software to place a gate in the sort of optimal location. So if I click the gate optimization tool, and we can specify, ungateable areas by axis or surface. So if we know that maybe we've got some A surfaces that we don't want, gates to be on, because that's going to be coming into contact with the user, or the user can see it, we can specify those surfaces. But then we can specify the number of gates, and then you click the run tool, and then the software will run through and basically place a gate where it thinks is optimal based on the number of gates that you're deciding on and any ungateable locations that you've decided. Again, we can use this sort of location that it gives us if we want to straight away, or we can use it as a guide, and then we can sort of manually assign it in the sort of vicinity that it's given us. So we can see where it's actually placed this gate. You might go, okay, so sort of maybe this area we want this gate, but maybe it's too close to a feature on the model, or it's not in an ideal place. So you could double click it and we can sort of move this gate, or you can just literally, okay, I can delete that gate if I don't want it there anymore. And I can just use my manual tool. I can say, okay, well, I want it in this area. I'm going to place it there, for example, and just manually put it there. We can then specify the gate size by diameter or radius, and we can change the shape to a rectangular in gate as well if we want. Obviously, any gates that are imported can be whatever shape and size that you wish. So moving on from there, the next tool in the window in the tab is this molding window tool. This will show us the window. So if I click that first to get it going, this will show us a window. That's why it's called the molding window, of the optimal fill time, melt temperature, and mold temperature. So it will show us if you were planning, show us, if you're trying to fill this in 3 seconds, that's not ideal. It's not going to work. If you're trying to fill it in 0.2 seconds, that's also might not work. And it will give us a nice window to sort of mold this in. So it gives us a nice molding injection, melt temperature, mold temperature, and fill time as well. And we can use these results in the advanced mode and also in the quick mode when actually getting some results. So again, this will run fairly quickly. In 10 to 20 seconds, we'll have some results. So we can see these results now. One thing you can see is a very quick sort of flow pattern. So you can sort of see that flow pattern there. And then we can see our molding window. we can play around with the mold temperature. We can change this to fill time, say mold temperature, and play around with the melt temperature, and obviously, you know, play around with these values. If I set that to mold temperature, I can then click a value within this green. Obviously, we can see not feasible, feasible, and preferred. So I want to obviously put something with the green. I can then potentially use these as a guide if I wish. You know, you can see 300 mold temperature, maybe 100, and a fill time of around under a second. If I click this update initial values, these will be taken into my quick run options, where we can specify just some quick machine parameters. Obviously, you can see the mold temperature, that melt temperature, and that fill time has been taken in. I'm also going to just run the quick one for sync marks as well. Click the run tool, and again, within around, this does depend on part. If you've got a crazy large part, crazy complicated part, it probably won't be as quick as this, but within 10 to 30 seconds, we'll actually have some results that we can then start to analyze. Again, we can then understand things like flow patterns. That might help us understand where we might need to put venting. We can understand whether this part, it thinks this part will actually fill okay, where we might get sink marks, and things like weld lines. So again, straight away, we've got some results. If I just change some of my animation settings, any of these things can be recorded. I'm just going to turn off shadows actually, because I'm not sure I like those. So any of these results that we see here can be recorded. We've got a slider bar we can play around with and sort of manually go. So we're just looking at the result type that we're looking at the moment is actually fill time. So we can understand last areas to fill. Other results that we can look at in this quick mode is confidence of fill. So we can see that this is all looking green, which is good. We can look at front temperatures, and we can put call outs on these. We can look at any pressure drops, weld lines, where we might see potential weld lines. So I'm not seeing any in mine, which is good. We can scroll that down. If you do have multiple gates, you can look at gate ID and gate contribution, so you can see actually what those gates are doing. We can look at quality of fill, shear rate, shear stress, a number of options. I'm not going to be able to go through every single result type, but hopefully you can see a few there. I can also look at potential areas where we might see sink marks. So I can see the areas where we might see some sink marks, obviously potentially in these sort of thicker areas. So we can see there is actually a thicker area sort of here. It's predicted we might get some there. Again, where our ribs are obviously slightly thicker, we might see some there. So we're starting to see some areas where we have some sink marks or potential sink marks. And that's the quick mode. So because it's so quick, hopefully you saw how quick it was to actually get results. That's why it's really good for exploration of things like gate positions and other results. We'll now go into the advanced mode. So I'm going to open up another part now. And in the advanced mode, we can study our injection molding process in more detail and study the 4 stages. So you've got your filling, your packing, your cooling, and your warpage stage. Very quickly, I'm just going to actually open up that part again and just show you how you can let the software quickly create a sort of a one or multi-cavity mold. And then I'll just show you how, if you have created your own method in your preferred CAD system, you can assign areas as well. So we're in the advanced mode now, and just going through the setup again. Let's just apply the same material and moving on to the runner system. We can apply, we've looked at gate optimization. We can apply gates, we can create runners, we can create hot runners, down sprues, injection points. We can also designate valve gates as well. But if I create a gate in that same sort of area, let me just also change my mold opening direction, and then I'll create the gate in the same sort of location I had it before. Again, we can play around with the size of that. If I now click the runner tool, we can let the software creators very quickly create a multi-cavity mold. So you can see 1, 2, 8, 4. If I click 2, it'll very quickly create this. All these parameters that we have here, like the sprues and everything, they are parametric, so we can play around with the height and all that sort of stuff. So that's just just want to quickly show you how you can quickly let the software just create you a quick multi-cavity mold. If I open up a model that already has, let's say, your method set up, we can then assign and create our sort of molding components, such as cooling lines, mold inserts, part inserts if we wish. So with this one, I'm just going to just get rid of a couple of things that might not be needed in here. Get rid of that. So you can see I've got my mold already set up. I've got my runners, my gates, all that set up, and I've actually got a few cooling lines as well. Using this tool here, we can automatically configure components, but also in the runner system, you can designate gates, you can designate your runners, designate your sprue, so you can use all these tools. If I click auto configure and just basically select an injection point, just confirm that these are the two sort of parts that I'm molding, specify your material and your grade, and then you're ready to go. So it automatically configures your gates, your runners, your sprue. As mentioned, we have got valve gates, we have got hot runners, but then we can move on to our tooling components. So we've got, first we can obviously create a mold. Again, specify your mold material, specify your mold temperature. You can play around with dimensions and other things. I'm just going to accept that. And then we've got part inserts. We can create these again in the software or designate them. And then we've got cooling lines. So cooling lines again can be brought in, and you can just specify cooling lines. This is great for standard cooling lines. We can also do conformal cooling lines as well. You can also create these in the software. So if I did want to create a cooling line, literally it's just a matter of, and you wanted to just sort of understand the effects of a cooling line in a certain area, it is just a matter of specifying where you wish. You can hold shift and that'll just give you a straight line. You can go anywhere you wish. Just to show you how simple it is, you can create just a 1 and you can accept that, or you can carry on and create more cooling lines. If you accept that, you can then specify your material. Again, really easy to create new materials, your temperature, radius of your cooling line, flow rate, and if they're starting and end times, if they are starting at a certain time within the analysis. So really easy to create cooling lines within the software. If I just accept that, we've looked at molding window, so I won't look at that, but then you've got your process parameters. Obviously, being able to sort of iteratively sort of change these parameters to sort of influence our results, can be, just as important as the method itself, in order to get good results, like increasing our packing time, maybe changing the fill time, all these sorts of things that the machine settings, if you can iteratively change those to get better results, obviously that's really, really important. So we can play around with our process parameters. So we've obviously got our filling parameters, initial melt temperature or injection temperature. We can play around with that. You've got your packing parameters, where we can obviously play around with the pressure. You've got your cooling time, injection temperature, and then you've also got your machine settings as well. So if you do use specific machine settings, you can actually then save these as whatever you wish. You can save it, and it'll save your machine settings. You can then use those settings later on down the line. So if you've got specific ones, but once you're happy with them, I won't go through all the process parameters in too much detail, but hopefully you've seen some things there that you recognize. Click OK, and then you're ready to move on to run your simulation. So now it's just a matter of going into your run analysis and choosing your mesh size. So choosing our element size, and then choosing the stages that we wish to actually study. So you can study just purely filling if you want. You can study filling and packing, packing and cooling, and also warpage. If your material does have fibers, obviously we can also understand fiber orientation, and we can also do cycling. Once you're happy with that, literally we would just be clicking the run tool and waiting for results, and then we can analyze the results and iteratively change them. This won't be as quick as the quick mode, but we'll get results. So for the purpose of this, I will have to open up another file, which I'll do now, and then we'll go through, just look at some of the result types and finish off and look at a couple more tools within the software. So we're going to look at some results now from this simulation. There's a number of results we can look at. We're going to start in the filling stage. Again, not going to be able to go through every single result type, just purely because we haven't got time. Hoping to sort of wrap this demo up in the next sort of 5 minutes, so we don't run over. But we're just going to go through some of the different sort of result types. So there's obviously the 4 stages that we've studied, and you can see this in our Analysis Explorer here. We can see we've got filling, packing, cooling, and warpage. Obviously, starting in the filling stage, a number of things that we can start to look at: temperature, pressures, fill time, velocities, air traps, mold temperature, numerous different result types that we can start to look at. I'm going to just obviously look at the flow pattern or fill pattern. Let's hit the play button, and we'll just analyze that so we can get an understanding of that. Obviously, this is based on a temperature value, so we can start to see the flow pattern, areas to fill, last areas to fill, and that sort of thing. Obviously, any result can be manipulated in terms of speed. We can actually take recordings of individual results, choose custom durations, and play around with your animation settings. We can also create reports, which I'll show you in a second. So literally, that's your sort of flow pattern of the part filling. Other useful results in the filling, obviously, I mean, they're all can be useful, but the things that you might be looking at are, is any areas freezing off before the part's filled? So you can start to look at potential frozen layers. So we can see areas like this, and you can put sort of call outs on these and start to understand areas that maybe are freezing off. We can look at air traps. Obviously, this is very useful for helping us to understand where we might need to apply venting. So obviously, molding simulation, it's an iterative process. You might run your first one, and then you might go, okay, well, that's where I'm going to get air traps. Let me apply some ventings around these areas and run it again and see what happens. So we can see we're getting some obviously last areas to fill. We'd obviously need some venting along probably the split lines around here. Also in the the ribs that we've created, we can see that we've maybe getting a little bit of trapped air there as well, and down the bottom here again, last areas to fill. So air traps are appearing, trapped areas appearing sort of in some of the places where we'd expect, but then also it guides us on where we might need to apply some venting. We can look at velocities, as the material's entering the part. But I'm going to just jump on to another result type, packing. Again, numerous results that we can look at in here. I'll just fly through them. The one thing that we might be interested in the packing stage is our sink marks. If we're seeing sink marks, can we maybe increase the packing? Other things, obviously things like weld lines and that. Let's just go and have a look at which were in the filling stage, which obviously might be important. But we can have a look at sink marks, and what you'll notice on this one, I've actually put some cooling lines on like sort of half the model, and obviously not on the other half. which you can see here, just to see what the effect of that might be. So we can see that we're getting some sink marks here, but we can get a bit of a call out and actually see the size of them. So we can see the actual maximum sink mark size is 0.1 mil, so it might not be too much of an issue, probably barely visible in that instance, but we can see where these might be, and we can obviously again put any call outs on the part to understand values in certain areas. Again, a lot more things that we can study in that stage. Going into, I have to go back into the filling stage, and I'm just show weld lines, see if there's any weld lines appearing anywhere. And then we'll look at cooling and warpage. So we can start to see where these weld lines may occur, so that again can potentially guide us in how we want to fill this part. So number of results, cooling, purely looking at how the part cools, and then we can look at warpage as well. So different results within the cooling, look at mold temperatures, densities, frozen layers as the part's cooling, temperature as the part's cooling. Finally, just going to jump onto warpage. We can see the warpage of this part. So we can see the maximum amount of warpage is 1.7 mil, obviously sort of here. What you'll notice is obviously we've actually got more sort of warpage on this left hand side where we've got these cooling lines, and sort of slightly less on the right hand side. Maybe that cooling line is causing that. What we can do in the software is actually create compensated geometry. So we can actually compensate and create a compensated part that then sort of warps into the that if you use the same method, that would warp into the desired sort of shape. So you can literally click this button here, it exports an STL file. This would give you something that looks like this. So if I bring this back to what the part looks like, you can sort of see it overlaid. The silver part is the compensated part, the blue part underneath is the original sort of geometry, and we can see that it would hopefully warp into the shape that we wish. So we can see that there. So that's what that compensated geometry does. We can also create reports, so you can actually generate quick reports. This can either be PowerPoints or PDFs, and then you can choose what things you're seeing in the reports, what views you're using. Obviously, you can create custom views and the result types, and whether you want to include animations as well, so all different result types in different stages. This would look something like this. Obviously, you can customize the report to have your logos and your PowerPoint sort of thing, so you can have it all as you wish. But then you'll have views and different animations in the reports and all the result types that you wish to sort of show. So that's the reports. So different types of things you can see in there. That is, I know I've flown through the results. Obviously, results are very important. I'm just wary that we might not have time. So I just want to make sure we've got a bit of time for questions. But I'm going to finish off the webinar, the demonstration there. I'm going to pass you back to Rob just to finish off, and then if there's any questions, we'll answer them now as well. Obviously, if you do have any questions about any more result types in more detail, just get in touch and we'll be happy to answer.